Today, I'm going to be talking about an applied problem that we have in finance. For example, in my case, I'm coming from a Dutch bank, ABN AMRO. We also have subsidiaries in Germany. We are particularly working in private banking. That's a sector of banking that you have clients with high net worth value. And the idea is to put the problem at the center and see what tools and techniques we need to apply so that the challenges from the business setting could be addressed. This is a personal account, not intended as advice or recommendation. The outline of the talk is I will be providing you a little bit of the business setting that I had, some theory about causal effect estimation, results and evaluation, and a summary. Let's start with the business setting. So wealth planning, that's a service that financial institutions provide to their clients. And it's tailored insight, and it aims to contribute to the clients developing, maintaining, or transferring their wealth. And these are high net value clients. And the insight can influence clients' investment strategies and behavior. The insight is provided as a meeting and a report. So this is how we are going to be showing it in this talk. So this is the treatment in the literature of, let's say, causal inference. And the business question that we are trying to answer is, what is the impact of the wealth planning insight on clients' investment behavior? And of course, when we talk about investment behavior, that's a little bit generic. So how can we measure this impact and quantify that? Because you could do this quantification of an investment behavior via different KPIs. So let's look into that. A wealth planning is provided as an insight to the client, which impacts their investing. So if a client is not investing, they could start investing. That's a binary outcome. So, and this impact happens after a certain amount of time. Let's say a wealth planning insight is provided, the meeting, the report, and the client takes this action of whether investing or not as a binary after a certain amount of time. Afterward, the client could bring also asset to their investment product. And of course, that could also take some time. So they're not going to immediately bring all the assets. They're going to probably gradually start building up their portfolio. And that also shows and could be quantified, a variable to quantify the impact. And that's a time series outcome. So we have different modalities here, you see, in our effect propagation. So you saw from the beginning we had wealth planning and how the effect of wealth planning propagates through multiple business KPIs throughout time. And then, of course, depending on the revenue structure, fee-based, transaction, whatever, you have some revenue and profit coming up to the institutes offering these products, and of course, a lifetime value, which you can even go further than 1 year. You can go 2, 3, 4, 7, whatever years. What's the impact of this treatment? Of course, there are many variables impacting your wealth planning, your outcomes. And if you see that, the complexity becomes more and more if you move from your, for example, binary outcome all the way to a lifetime value. So the approach that I'm going to be focusing on is I'm going to quantify the impact for investing and invested asset to those two outcomes. But of course, you can translate as an indication those outcomes throughout the other KPIs. So if you see this, this is our causal model. So we have a confounder impacting the treatment and outcome, and these confounders could be different variables: age, sex, clients, relationships, so on and so forth. Well, okay, what are the challenges imposed by the business setting? Of course, the golden standard of causal inference is A/B testing, or like randomized controlled trial. However, in this case, it was not feasible. Why? It was unfair, because you couldn't deny certain clients to receive this insight. So that was one of the limitations. Another one was some clients would kind of proactively seek this, this insight. So then you have self-selection bias. Another challenge is the units or relationship graph of individuals and companies. So if you look at the, let's say this is by financial sector considered as like one client unit. Then you have like the head of the, let's say, the family here in the center, then you have the children, and then you have the company of the father, you have the mother, the company of the mother, then you have the son-in-law, daughter-in-law, like they have also their own company, then you have a complex graph. Okay, then you provide the treatment to a certain node in this complex graph, good luck finding the impact. So how far should I go in this complex network to identify which of these nodes are impacted? Then, of course, what are the impacted subgraph? That's the notion of course, you want to quantify with your domain experts. So this is the identified subgroup that so these are the nodes and relationship in vicinity of the treated node that was discussed with the domain experts, and they identified this. So we didn't use sophisticated tools or techniques from data science to do that. And then, of course, there is another challenge, the various treatment timing. So majority of the work done in causal inference, you have one treated group, one control meet, and then you have one time the treatment is kicking in. But what if the treatment happens throughout time, every month? Then you have various treatment timing. So all of these challenges are very different than the standard setting that you see in the books and literature that being addressed when you're dealing with practical problems. Okay, a little bit about the theory of causal estimation, estimands, and identification assumptions. There are two estimands very famous in causal inference. Average treatment effect and average treatment effect on the treated. So ATE and ATT. They are answering different business questions. ATE talks about policy implementation. ATT speaks about policy evaluation. The business setting that we have, we want to evaluate impact. So we are talking about ATT. Of course, if you are thinking about, okay, now the impact is positive, I want to roll out this treatment to my other, let's say, client base, the controls, then you need to be having insight on ATE, so which is a little bit more strict. Let's look at and visit the assumptions in causal inference. There are some basic and generic assumptions that needs to hold. That's non-interference. That means if you're providing the treatment to your treated group, the people in your control wouldn't randomly find that insight and start applying it into their own case. That's one of the basics of the assumptions that we need to identify identification, to make the identification from causal estimand to a statistical estimand. Another one that we need is consistency. What is consistency? Consistency says that you need to have one version of treatment. So in our case, we had a well planning, which was a meeting and, let's say, inside report, but also only a meeting. So then what I did, we put those, let's say, treatments that were only meeting out because there was a different version from both the treatment and control. You need to also have some other assumptions if you're working with the binary data modality. You need to have positivity. In the context of ATT, it means for any treated unit, you also have a comparable untreated unit. You have exchangeability. That means before applying treatment, the group that you want to treat, on average, if you compare it with the control, you flip that, you would have a same outcome. If you go to the time series data modality, you have some other assumptions like non-anticipation. So you remember there was COVID, there was lockdown happening. Let's assume that this T is the time that because of lockdown, all the shops going to be closed. And then people anticipate that because they hear it from news and they rush into the stores to buy stuff. So if you are looking into the impact of COVID on consumption, then you need to know about this non-anticipation effect, that you see the curves jumping up before the treatment kicks in. We don't have that here, luckily, but if you have, you need to address it. A parallel trend assumption, before treatment, the group that you have that are not treated, if you compare it with the group that's treated, the evolution of their outcomes should be the same on average. So these are the assumptions you need. If you look at this a little bit carefully, in different data modality, the latter assumption is more like the same. It's a dual. All right. So we shared about the business setting. We shared some basics about causal inference. Now, we want to mimic and address, so we want to address those challenges that I mentioned before. One of those challenges was we were not having the golden standard A/B testing. So we want to mimic that. Okay, how? If you have randomization, you would have this beautiful causal model that your T impacts Y, and also there might be some X that impacting Y, but there is no relationship from your variables to the T. If there's no randomization, this is what you're going to get. There are some always variables that impact your treatment because it was not fully randomized. So you might have certain age groups, certain characteristics in your treatment or control a little bit more bolded. And that's problematic, and that's bias. Why? Because it opens a backdoor path from your treatment via those confounders as an association to your Y. And it fully pollutes the causal association that moves from T to Y via this confounding association. So what is the answer? Try to block that relationship from X to T. How? By modeling that. So here the T is a binary outcome. It's either treatment is given or not. So if you, I'm not using anything more complex than linear regression and logistic regression in this talk. So if you have T as an outcome, then you need to fit logistic regression with an input of X, then you will model propensity, and this gives you the treatment assignment mechanism, the unbalancedness between your treatment and control with respect to the covariates. So you can use two techniques. Okay, there are multiple, two famous, matching and propensity, inverse propensity weighting to decouple this. I'll be focusing on the matching one. Here I'm going to be giving you a little bit of a flavor of the pseudo algorithm I'm using to simplify that network and mimic network structure. So per time quarter, we will have a treatment. We have a pool of those networks, complex networks as our treatment. So each one of those networks is, let's say, client or sample. Also, you have that similarly in your control. Then you would fit a logistic regression where the T is the outcome, X is the covariates, and you're doing this at node level. So you're doing this for all of the nodes in those networks. Then you would match a control twin to every treated node with the first nearest neighbor. And that's the positivity assumption. Yeah, you remember on the first slide I was talking about, for every treated unit, you need to have a comparable control. That's where you need it here, because you would sort those nodes here based on their propensity score. That means, literally put, the probability that node is belonging to the treatment, match it with another node in the control that could also be belonging to the treatment. So then you have 80%, let's say 2 nodes, they were having 80% chance of being part of the treatment. Fantastic. You match that as a control. You do this all the way down, then you have a balance of the treatments of the nodes that have the similar likelihood to receiving the treatment in your treatment and the control. Then you would combine the match node and their adjacent nodes, that subgraph that we, based on domain knowledge, identified here. And then the aggregated nodes will shape your treatment and control assignment. And what you see here, we went from all the way from a network of entities to a unit. We achieved two things. We simplified the business question, and we also mimic randomization. But if we look at the histograms of the variables, we see quite some alignment on the distributions for some covariates. However, that's also not the case for some other. And that is the caveat of matching method. We use matching because of its simplification, so it's a simple tool. However, that comes with a cost because there are bias associated. And if you have a lot of data, that mismatch would propagate. But of course, there are some bias correction methods. Also, the curse of dimensionality holds here because when you have more and more covariates, it's more difficult to match. If you have only age, you can easier match two units from 2 different groups. If you have age, I don't know, sex, and then next to that relationship, client segment, whatever, it becomes a little bit more difficult. So this is the theory we need for the binary outcome modality. What about for the time series outcome modality? To deal with that, and also we are now in the observational setting. Remember, we are not randomized. Many of these tools and techniques would be irrelevant when you have that beautiful randomization, which of course came with a cost in our situation, which was not possible. We want to estimate the causal effect of treatment on time-varying outcome. We have a control group. It's changing throughout time. You have a treatment group also changing throughout time. Then you have a time that the treatment kicks in. And then we see, for example, afterward, the treatment goes up. The difference in difference, as you see, there are two difference terms in the name. The first difference is talking about the post versus pre-treatment. So if you see, for the treatment group, this green arrow, that's the uplift from the pre to post value, also for the control, pre to post. And then you have another difference, that if the parallel trend assumption holds, you would see that it gives you the average treatment effect on the treated. So if you look at it, it's the uplift from these dots, which is kind of the counterfactual value if for the treated group, if they were not treated, using the control. Okay, this is interesting. However, does it solve all of our problem? Well, it kind of gives us the hint, but still we have an issue here. We have the treatment assignment happening on regular basis every month. It's not just this beautiful setting that you would have a nice treatment and control and then one-time treatment. This insight is being given to the group of clients, cohort of clients every month. So how can we deal with that? Luckily, with the advancements on difference in difference, there was a recent work called as a staggered difference in difference, a result shared by Calloway and Santana in 21. How they approached this was they applied the difference in difference method to analyze different cohorts against the control and combine the results. It's very intuitive, right? So, but the thing is, then you need to have either a unique control for all of those treatments, or maybe you can also use the late treated as a control. The parallel trend assumption that we spoke about, it's crucial in this setting to retrieve the average treatment effect on the treated. To inspect that and check that, you can do it visually. So if you look at this graph, on the x-axis I have time, on the y-axis I have the invested asset. So I'm talking about how much asset is brought into the investment product. The control group, that's a control group, let's say clean segregation, never treated as a control for all of these treated cohorts. You see that, don't look at the starting points, but there might be jump up and down, but look at the trends. You see that some of these cohorts are following the trend of the control. However, there are also some that they're not following. So you're going to be in a good shape for those that are following, and not really in a good shape with your estimation. You might have bias for those that are not satisfying this assumption. So one way of doing this, let's say, inspection is via visually, but there are also other methods to do this via the test plots by Calloway and Santana in their package that they propose. Okay, results. You remember that in the beginning, we used this propensity score matching to cancel out the relationship from the X to T. Now we are left with the causal association. So for the non-investing units, we will fit a model from the outcome Y to T. The average treatment effect would be an uplift from if you would do a cutoff of a time, because conversion as an investing or not, it's a time, of course, you could do 2 months time, you might have certain group of clients, you could do 3 months time, after 3 months, you would have probably more because the curves keep rising. The longer you wait, your conversion curve is going to be going higher and higher. Of course, you want to have a relevant cutoff. It shouldn't be too small, shouldn't be too big, it should be relevant, that would not include other biases. Yeah, so something also to be discussed with your stakeholders, but also looking at the curves. Then for the already investing units, you would model your outcome with the treatment and the post-treatment dummy, and then that would give you the uplift here, average treatment effect. Of course, then you also need a cutoff after treatment. We didn't go very far to have the effect of many confounders coming in, so probably 2-3 months after the treatment would be fine. All right. We discussed about the challenges, we discussed about how to address those challenges, we showed some insights from and flavor from the results. Now, always there's a question, how can we evaluate if this is correct or not? And I want to approach this evaluation from different perspectives. Okay, why it's relevant? In real life, there is no true effect to compare with. So majority of the works that you see either in papers, books, they are doing causal inference with simulated and synthetic data. There, they are they're doing the simulation with a true effect, so they have that true effect. And they would do a causal effect estimation and they compare it with the true effect that they already know. However, in practice, that's not known. So all of those things you see in the books and literature don't apply in practice. So how could you take care of all of these, let's say, biases and issues that could come on your way? Some part could be addressed from a business perspective. I know as a data scientist, we are always excited about tools and techniques, and we sometimes underestimate the business perspective and business rules. But treatment assignment rules, if they're also replicated for your control pool, they are also a good thing to minimize bias. Domain expert knowledge to identify the effect and where to look for the effect and how the effect gets propagated. Those beginning slides that I was showing you a graph, how you do, how you identify those subgraphs, how that visual diagram, directed graph would flow. Those are things that you want to double check with your business partners. But of course, from a data science perspective, and you can do effect estimation and compare that with other treatments. So there might be, for example, investment campaign. Let's see how is that doing compared to this one. Validating your identification assumption, parallel trend, non-anticipation. Sensitivity analysis and introducing bounds around your effect estimation. Comparing different and other models as well, like W robust. That's a good one that combines also elements from the propensity score and potential outcome with outcome modeling. So with this said, just a quick recap. We had a business problem at hand, and we wanted to define what are the steps we need to take to address those challenges. One of those challenges was to translate that network structure of entities, which was very complex, to units. We did that. The tools and techniques used was explained. Then we needed to randomize, mimic randomization. We used propensity score, and with matching, we blocked that relationship from X to T. And then we used effect estimation of wealth planning on multiple KPI. And multiple KPI is relevant. I don't have time a lot to discuss that. It could happen if you miss one of these KPIs, you are missing part of your impact. So it's always good to have a holistic vision on what are the KPIs, and in practice, it's not one KPI. You need to do causal inference on multiple KPIs. And that was what we looked at. For a group of clients, we needed, let's say, a binary outcome to look at. For a group of clients, we need a time series. And it's even more than that. I tried to a little bit simplify it here. If you're interested to read further about the topic of causal inference as a theory, these are the resources I would suggest. With that said, thank you very much for your attention.
Thank you, Daniel. So we have 2 questions from the app. The first one, how did you get clients to review all nodes in their group? Connected assets in a family?
Sorry, how did I get what?
Yeah, how did you get clients to review all nodes in their group? So this is the first question.
So before you move to the second, so I assume that the discussion is, I'm not fully sure if I understand the question, but How did I manage to get the clients in the...
Yeah, I'm just reading as how did you get clients to review all nodes in their group? Then there is a comment, connected assets in a family.
Okay, so this is our database. So we know the bankers that are in connection with the clients, they know who is the father, who is the son, who are the companies. So we have that as our disposer.
Perfect, thank you. There is a second question. How do you decide the optimal time frame for the cutoff?
Okay, thank you very much. That is twofold. One fold is looking at the business setting, asking your domain experts. Because, for example, when you have, for certain product, you do the treatment, they know, based on the business setting, how long it takes because of the processes that the client might have online, with filing application, how long it takes until that the product is administered. So based on experience, the domain experts have insight on that. Another method is using data science and looking at your curves. So for example, for binary outcome, when I plotted the curves, by the way, this is not a real curve, it's just like a mimic of that. So you would see a first wave, second wave, third wave of conversion, and finally your curves plateaus. So for me, somewhere between the second wave and third wave of conversions is the right cutoff based on data science point of view, which was close to the domain knowledge point of view.
Thank you. Can you clarify in your design, all your participants get the wealth training, and then your control group are those that do not invest? Is that correct?
The control group are those clients that they don't receive this insight. However, they can still invest. So they might be totally unaware of wealth planning insight, because that's an insight given to the clients, how they can grow their wealth. But they might be fully unaware of that, but still they would say, oh, okay, I want to be investing because it's a good market. So the market impact is also one of the confounders. So they could definitely, without even having this insight of wealth planning, do investment.
So the control group are those that get a different type of wealth planning?
The control group is the clients that never get wealth planning.
Okay.
So the treatment, so that's in causal inference, okay. You look at the treatment, the group that receives treatment, and then you have control the group never receives treatment.
So it's those clients that decide not to get the wealth planning.
Well, it's not their decision, because then you have also bias. It was not happening.
Okay.
Maybe they were not aware. It's not that they didn't decide. Maybe they would have if they knew about it.
But the key point is they're not randomized to those groups.
Exactly. That's the issue. They're not randomized, and that's the whole idea with the challenges posed because of absence of randomization. Indeed.
Okay, thank you. So we have 2 minutes left and 3 questions here. So the first one, do you use a graph database for your data? And if so, which one?
We are as an organization, probably yes. As me, no. I'm using the data as it is, as SQL, and you don't really need that sophisticated tool for this analysis.
Perfect. The second question, what was the magnitude of the treatment measured in this specific experiment? Okay,
that's a very good question. I can't answer that. So these are, sorry for that. So this is a real life problem. And to be able to present the results, I have to make it, because it's confidential insight, so I have to separate the business insight from the tools and techniques. So I'm just trying to give the flavor of an applied project doing with data science and causal inference. I can't really give the juice of the insights. Sorry.
It seems like such a noisy setup in a way. So you're measuring something that's very far away. So it's something that significantly measurement from a business perspective and would have an impact?
It was, so it had impact, the impact was positive. And it was statistically significant, if that answers. I can share that.
Okay, thank you. And one last question, because we are over time already. Was the study able to review good, useful interventions that surprise subject that matters experts?
Sorry, once again?
Sorry, I'm going to read again. Was the student able to review good, useful interventions that surprised subject matters experts?
This was a positive intervention, and the outcome was very interesting to the business. So there were some insight coming out of this, especially with this multi-KPI evaluation that they were not expecting, and so there were business processes being improved also internally based on this insight.
Thank you very much. Sorry, unfortunately, we don't have much time. So
please feel free to reach out. I will be around if you want to further discuss this, and if you have, maybe I can have more flexibility behind, not being behind a video, to share more stuff. So yeah.
Thank you very much.
Cheers. Thanks.